I was recently working on a problem like this, a pre-calculus problem where you have to expand this out to some long polynomial, and you're often given the binomial theorem, which is this mess, and you then have to identify the n, the k, the a, the b, and all this stuff. And I was thinking, yeah, there's got to be an easier way than this, and there is, and it's called Pascal's triangle. Now, this is for like an exponent of, I don't know, maybe I wouldn't go past 6 or something like that, but for 5 and fewer, I think this is way easier. I'll show you how it works. First, we have to look at what? This is to the 5th power, so this would be 1, that'd be 0, 1, 2, 3, 4, 5. So we're looking at this one right here. So this would be our, this line right here. These are the coefficients of our expanded polynomial. And so we have 1, and then we're going to have, I'm going to leave some space here, and then plus 5 for our second one, plus some stuff in between, 10, plus some other stuff in between, and then plus, I'm running out of space here, so plus 5 and some space in between, and then plus 1. So what I see first is I have to put this 3x right here. So we have these two items. Each of these have to be components of each of the terms. So the first one's going to be to the 5th power, 3x to the 5th power. So I'll just put in that 3x, and all of that is being taken to the 5th power. And the y to the second is being taken to the 0th power. So I'll deal with that. Then we have, I pause here because maybe I'll make this green to talk about that exponent and what's happening with that. So on the next term, we have the 3x. So this is times 3x and a y to the second. But the x terms are declining in value. So this would be to the 4th, and this would be to the 1st. And then we'll go, there's a 3x component. There's actually a 3x component in each of these. And there is a y squared component. And then the x components, or the exponent on those components, are going from 5 to 4 to 3 to 2 to 1 to 0. And the y component of each term is increasing. 0, 1, 2, 3, 4, 5. And now we clean things up. So I'll put it all in maybe the red. I'll take care of each of the, let's see, 3x to the 5th power. So 3 to the 5th power, 3 to the 1st is 3, 9, 27, 81. I forgot what 81 to the 3rd. 81, 240, oh my God, 81 times 3, 243. So 243x to the 5th is that first one. And then we have 3 to the 4th, which should be 81. So this would be 81x to the 4th. And then 3 to the 3rd is 27x to the 3rd. 3 to the 2nd is 9x squared. 3 to the 1st is just 3x. And 3 to the 0 is just 1. I won't even put anything there. And we have to make sure that we'll also do the y components. So I'll do that too. And that means y to 0 to the y to the 2nd to the 0. That's just times 1, because anything to the 0 power is 1. And then this is y to the second. And this is y to the 4th. This is y to the 6th. This is y to the 8th. And this is y to the 10th. And I probably could have put 1 at the very end, although it doesn't really matter all that much. This is 1 times that, okay? And if I were to give all those coefficients as well, plus 5 times that, plus 10 times that, plus 10 times that, plus 5 times that, plus 1 times that. In the end, I have, what, at the beginning it's 243x to the 5th, and then plus 405 x to the 4th, y to the 2nd, plus 270 x to the 3rd, y to the 4th, plus 90 x to the 2nd, y to the 6th, plus 15 x, y to the 8th, and plus 1, or just plus y to the, I believe that is 10th. And there you go. Holy cow. I'll bring this up a little bit to show that is the final polynomial. And I think that's a little bit easier than using the binomial theorem. And so for powers of 5 or fewer, that's my call for creating those polynomials. Enjoy.